Hi, welcome back to Game Innovation. I want you to consider this scenario. You dream up a concept. It can be as strange or absurd as you like. Let's go with something simple for now, like gravity-resistant cupcakes to use in a whimsical and imaginative game setting. Imagine you could input that into a prompt box and then instantly see it come to life in Unreal Engine. An entire scene, perhaps even an entire game, all from one prompt. Now, in all likelihood, the final product probably wouldn't be perfect or even usable immediately. In this case, for example, these cupcakes are clearly not gravity resistant. So what if the tool that brought your prompt to life was also interpretable? If you could read through its reasoning, what tasks it deemed necessary, and how it planned to complete them, and you could then manually tune, trim, or branch off ideas from this action plan to produce results closer to what you intended. This is the tool at the heart of this week's paper. Dream Garden, a designer assistant for growing games from a single prompt, by Sam Earle and collaborators. The final paper in our short series on NYU's Game Innovation Lab. The paper was also developed in collaboration with UT Austin and Microsoft. Given not only the stature of who is involved with this research, but also what this tool is trying to accomplish, it seems imperative to discuss both the motivation and potential impact of a tool like this. Heavily automating game design is a very divisive topic, and of everything we've covered to date in this series, this is perhaps the most contentious among artists and developers who oppose the use of AI in the games industry. That is, of course, a stance that should be acknowledged when discussing this work, but to get to that, we first need to understand the full details of Dream Garden and where its merits lie. The basic appeal of Dream Garden is clear. Creating content in a game engine can be quite a long, iterative, repetitive process, and incorporating AI into that pipeline can sometimes add to that arduous nature. For instance, using an LLM for code generation often means a loop of trial and error, copying the code into Unreal, getting bugs, tweaking the prompt, getting code again, and repeating. Other aspects of game creation, such as obtaining assets and setting up scenes, can also be a time-consuming process, especially for newer designers. But Dream Garden streamlines all of this by automating not just asset generation, but also scene generation and code debugging. This makes the process of vibe coding faster and less frustrating. And interestingly, that automation process doesn't actually require the development of any new, novel AI models. It instead requires a connected pipeline between existing tools and a navigable user interface. The magic of Dream Garden isn't in performing any one specialized task, but in connecting every element in the process seamlessly. So let's look at exactly how those elements come together. To start, an open-ended idea is fed into an LLM, which interprets the language and uses its knowledge of Unreal to create a structured plan. It then recursively breaks down this plan into finer steps until it reaches leaf nodes, which are concrete implementation tasks that can be executed by the system. In Dream Garden's current form, there are 3 such tasks it can perform: downloading meshes from a dataset, generating new assets when no suitable ones exist, and producing code snippets. In future versions, new task types could be introduced, such as a submodule for spatial reasoning, which the current system still struggles with. Let's take a deeper look into one of these submodules, downloading assets. This involves searching through the Objiverse dataset, which contains hundreds of thousands of 3D objects that come with text captions. To find the right asset to download, Dream Garden uses a pre-trained model called Clip, which was trained on image-text pairs to embed both into a shared vector space. Dream Garden embeds the images and captions from Objiverse into the space, then takes the new prompt, embeds that too, and selects the closest match by measuring vector distance. It then downloads the mesh, loads it into Unreal, and lets the code generator know that it has access to this mesh if it ever needs to make use of it. This is an extremely convenient process that can typically get in the right ballpark of what it's asked for, but may not always align perfectly with what the user intended. In one such example, the text prompt asked for a textured bakery interior, and the output instead was the interior of an ice cream shop. If the planner instead believes that an asset likely won't have a close enough match in the Objaverse dataset, it can instead run a different submodule, generating assets. This once again uses popular, pre-existing methods and stitches them together, first generating an image using DALL-E, then using an off-the-shelf 2D to 3D image converter, and then downloading the 3D object into Unreal just like before. These pre-existing or generated assets are then available to be called and manipulated by the code-generating submodule, which can establish key behaviors and attributes of the simulation. We can see all of this in action in this demo, where the user asks for a simulation of a spaceship flying around the sky, abducting cows and other animals in an enclosure behind a farm. This triggers Dream Garden's recursive process. It interprets the idea, breaks it into implementation steps, and executes tasks using its 3 submodules. If errors occur, they're automatically handled through a feedback loop. The final result is a grassy Unreal Engine scene with primitives representing cows, a flying spaceship mesh, and a working abduction mechanic, all from a single prompt. Now, even in this form, the results are impressive, but Dream Garden was also designed with user interactions in mind. Specifically, it focuses on 3 crucial methods of user interaction. The first is dreaming, where the user can express open-ended ideas and input them into the planning module. Essentially, this is the initial free-form prompt. Then there's gardening, where the user can explore the action plan and decide what to expand or prune. For instance, in the cow example, one particular leaf node asks the system to generate other animal assets, for example sheep, pigs, and chickens. Since the tool is designed to only generate one asset for each leaf node, it will choose only one of these animals by default. But if the user unchecks the node as a leaf, the system can branch out more and generate multiple other animal assets. Or, if that's too much variety, the user can also trim the idea back down. Finally, there's building, where direct edits and additions can be made to the final output, including to code samples and the overall environment. Again, in our example, the user can decide to not include an element like this green debug sphere and hop directly into the generated code to remove this detail. They can also give direct, written feedback to any point in the system, for example, asking the final simulation to use actual cow and sheep assets instead of generic cubes, and we can see the system has worked to implement this feedback in a new, refined version of the output. And now that we understand how Dream Garden works, we can finally get back around to some of our bigger questions from the beginning. Particularly, what's the point of all of this? What's the point of automating this process when what's produced still isn't viable for full game development yet? The results are undeniably impressive for a single prompt, and the feedback loop is seamless. But realistically, the best outcome today is a small, self-contained, unpolished simulation. So why pursue this? Well, one surprising motivation behind Dream Garden was actually to develop more grounded AI agents. Today's large language models often generate plausible-sounding outputs without real-world grounding, which can lead to inaccuracies or hallucinations. Dream Garden serves as a step towards automatically generating diverse, game-like learning environments, spaces where agents must interact with consequences and physical constraints. As the lead researcher Sam Earle puts it, let them die 1,000 deaths until they learn the meaning of the word lava. In other words, Dream Garden aims to make agents more robust and reliable by grounding their learning in simulated experience. In addition to this, the researchers were also just as interested in where the system broke as to where it worked. All the strange, unexpected outputs, like half-functional simulations or surreal environments, could potentially act as a form of 3D concept art, which makes Dream Garden good for exploring the boundary cases that stretch what generative systems can do. In fact, the opening cupcake example was a direct request from a user interacting with the tool live at Kai, and despite the output being, ironically, a little half-baked, the user did enjoy seeing a form of their idea realized in a real, physical space. In the paper's Kai presentation, there was also a reference to a term coined by Dr. Kate Compton, a Bach faucet, which she describes as a situation where a generative system makes an endless supply of some content at or above the quality of some culturally valued original, but the endless supply of it makes it no longer rare and thus less valuable. A recent example of this is the Studio Ghibli art trend, where a style that was considered unique and artistically valuable became an overflowing commodity and therefore ruined its value. In Dream Garden's case, however, it's been declared as a self-proclaimed slop faucet, not even meeting the standards of typical small game projects, and instead producing an endless amount of messy, experimental, boundary-stretching ideas in fully simulated environments. The value then came from discovering the edge cases and finding meaning in the mess. Given that goal, it certainly seems like Dream Garden is not as much of an imminent threat to human designers as the initial premise might suggest. In fact, some aspects of the tool could be immensely valuable in human-led creative workflows. The researchers emphasize the importance of the gardening phase. Users can expand, prune, or revisit branches in the planning tree. And in a brief user study, many participants found watching the plan unfold to be enjoyable and illuminating, even if the results weren't always exactly as they envisioned. They were also able to take charge of the creative process while the tool handled the busy work, which is an ideal form of collaboration as AI continues to advance. That said, there's still an open question about how much control users truly have. Since the LLM generates the initial structure, it may subtly steer users towards accepting a predefined framework, encouraging passivity over creative authorship. So will tools like this empower new kinds of creativity or make users more reliant on what the model suggests? That remains an open and fascinating question. The potential impact of Dream Garden and future tools that may take inspiration from it are broad and highly debatable, and I encourage you to share your personal opinions in the comments. Its motivations, both direct and ulterior, are important to explore as AI becomes more prevalent in game design, yet it also lies at the heart of one of the most contentious issues of the modern day in mass-produced generative content. It invites us to think differently about authorship, automation, and the limits of our tools, while giving us the opportunity to glimpse into the potential future of creative workflows. I'd love to see how you all personally feel on the topic. If you enjoyed this quick dive into Dream Garden, make sure to subscribe and check out the full paper in the description below. You can also watch the previous 2 videos on new AI tools in the game space, and be on the lookout for more videos which will cover new advancements in game design and technology.